We are going to start our learning of Math 1332 with estimation, graphs, and mathematical models. Now, the good news is this first chapter of Math 1332 is not extremely challenging or anything. It is it's not straight on review, but it's probably stuff you've seen before or can get comfortable with. So we're not going to hit the ground running too hard here, I think. So what we need to talk about is a very, very important field in mathematics called estimation. Estimation, the process of arriving at an approximate answer to a question. Here's some ways you can estimate. You can round your numbers. That's going to be huge. How many of you have rounded a number before? You rounded to the nearest tenth, nearest hundredth, 2 decimal places. Yeah, we're going to talk about the theory behind rounding a little bit. It's pretty straightforward. Remember, when rounding, you look at the digit you want to round to, and then you look one place to the right of it. If that digit to the right of it is 0 to 4, you're going to be rounding down. If that digit to the right of it is 5 through 9, you're going to be rounding up. So rounding numbers, that's opposed to truncating numbers, which is where you pick your digit and then you just cut off everything to the right and you don't round or anything, which is to say you're always rounding down when you truncate numbers, and that's not what we're going to do. Using graphs, that's going to be pretty important. Using mathematical models, that's also going to be important. A mathematical model, just think about what a model does, is it displays something for others to view. So a mathematical model is going to show us something, show us some kind of mathematical relationship or some kind of real world relationship that we use mathematics to really define. I'm going to talk about all those wonderful things today. Rounding whole numbers. Rounding whole numbers. So here what we're going to do with rounding, it looks like it's a really nasty process, but if you're comfortable with rounding and you know what you're doing, it actually makes a lot of sense. So again, your final exam, Tuesday and Wednesday of next week, that's March 2nd and 3rd. We are meeting in person and doing the paper exam on both days. So imagine you had this number. This is actually pi out to 5 decimal places, 6 significant figures. And let's say we want to round to the nearest hundredth. The nearest hundredth is going to be 2 places past the decimal point. Right there. This is going to be called our rounding digit, or rather it's the digit to be rounded. So you can think of John Wayne drawing a line in the sand at the Alamo. And he says, all right, this is as far as we're going to go there, Pilgrim. So you look at the digit to be rounded. Now, the 1 over here is going to be what tells us how to round. It's not quite going to jump ship and get in here and be safe, but it is going to give us some information. So that's the digit to be rounded. If you go 1 place to the right of it, this is the digit that tells us how to round. And that digit that tells us how to round is a 1. This digit is 1, so we round down. You round down if the digit is 0 to 4. And rounding down means you're going to go out to the digit to be rounded, 3.14. And if you round down, everything else gets cut off. We take it and we swipe everything else away. So it rounds down to 3.14159. In other words, you leave the digit to be rounded alone and you cut everything else off. Let's say you want to round not to the nearest hundredth, but the nearest 10,000th. Notice that D, or rather, yeah, the TH rather, that's what tells us it's after the decimal point. And we'll look at what those digits are in just a moment. We'll remind ourselves. We are going to take our dividing line now. Oh. We're going to take our dividing line and now put it right there. And now this is the digit to be rounded. It's now the 5, because when you go on decimal points, you have the 10th, the 100th, the 1,000th place, the 10,000th place, then you'd have the 100,000th, the millionth, the 10 millionth, the 100 millionth, and so on. So now the digit that's going to tell us how to round is now 9. Because it's one place just to the right of our digit to be rounded. Here it's a 9. Here this telling digit is a 9, which is between 5 and 9. So we round up. What rounding up will do means we'll have 3.141. We'll round the digit to be rounded. We'll add 1 to it. And then everything else to the right gets cut off. So you go one place to the right of the digit to be rounded, and that's your tell-all digit. And so there you go. You know, whenever I do this course, whenever I do any math course, I like to inject a little humor into it, because goodness gracious, sitting here and learning math for an hour and 20 minutes straight with no break, not only does it strain your brains, not because you aren't smart, but because sometimes you need a little pause, don't you? You need a little break. Guess what? It's the same thing for the person that is delivering the mathematics lecture. Here's a problem. There's two problems, really. One, as I've mentioned many, many times before, I'm not funny. I'm not a funny person. I try to be. I wish I could be, but it's just not a skill or a talent that I happen to have. So what do? Instead of being funny, I steal jokes from other comedians. The problem is, and here's problem two, a lot of this math, there's just not a lot of places to inject humor, is there? There's no weird puns I can make on rounding. Like rounding is, there's nothing. So it's a little bit of a problem. I want to inject more humor in, I promise you I do, but it's just not always feasible. This stuff's just a little bit dry, isn't it? Now, hopefully, when we get later on in the semester, there will be some funny observations I can make, or some jokes that I've stolen from other comedians that I can make. But unfortunately, this stuff, there's just not a lot of it. So that's my little meta-analysis of why I haven't been telling a lot of jokes recently. After you've done your rounding, you can use an equal sign that kind of looks more like two tildes, two squiggly marks. That means approximately equal to. Now you're saying we've rounded, so it's not the same number anymore. It is technically a different number, but it's close to what we want. It's close with how much precision we desire. So again, look at the digit to the right of where rounding is to occur. If that digit is 5 or greater, you're going to be rounding up. You're going to be adding 1 to the digit to be rounded, and then you replace all digits to the right with zeros. If you're already past the decimal point, that means nothing. You don't have to do it. However, if the digit to the right of the digit to be rounded is less than 5, is 0 through 4, you're going to be rounding down. So we'll do these examples here in a moment. Let's remember let's say we have a number. I'm going to write that number nice and large. Let's see, how about the number 41,750? 529.01567. That's a big number. I wrote it out emphatically with some spaces in between because we're going to talk about what all the different places are. The most basic place to start is the ones place. That's the digit in the ones column. Remember you'd learn the ones column, the tens column, the hundreds column, the thousands column, 10,000s, and so on. The reason that it's like that is because we have base 10 numbers, but that's a story for another time. So this is going to be the ones column. That's the ones column. What is this going to be here? The tens column. Yep. And this really makes me want to show you how base 10 numbers work. How what you're really saying is this is 4 times 10,000 plus 1 times 1,000 plus 5 times 100 plus 2 times 10 plus 9 times 1. And then you can also include the decimals and talk about how each place is a different power of 10. This is 10 to the 0th times 9. This is 10 to the 1st times 2, 10 to the 2nd times 5. But I won't go into that detail, but it is interesting because then you could talk about any base numbering system. You could talk about binary. But we just don't have time. You know, I have a friend who lives in Lubbock, and he teaches high school. And he's a math nerd like me, and he teaches high school math. And he was telling me when we sat down and we calculated the amount of time, a course that you normally take in college in one semester, fall or spring, say, is taken over the entire school year in high school, right? Like you'll take Algebra 2, and that's equal to roughly college algebra, something like that. But you'll take it in the fall and spring. In college, you only take it in one of those semesters, like the fall. On top of that, they also meet, I mean, you know, school meets 40 hours a week, high school, and they'll meet for their classes. They'll get like 4 to 5 hours a week that they're physically meeting for just that one class per week. In college here, we get less than 3 hours, if you think about it, that we meet each week, and we do it in half the time. So we did a little math, surprise, surprise, and we realized that my friend who teaches high school, he gets about 3 times as much face time with his students for the exact same class to cover the exact same material. Not always exactly, obviously in college we cover higher material, but to cover a lot of similar material, he gets 3 times as much time. So he'll have a class where they all play like RPG games together, and they're all role playing, you know, where you're like, you're the sheriff of this town and this is an outlaw, and you guys play a little stupid math game out of that. He gets time to do that kind of stuff because he's just, you know, it's wonderful. You got 3 times as much face time with the students. We do not have the luxury of that, and I have lamented this fact many, many times, but that's just how it is, isn't it? How many of you wouldn't, look, obviously you don't want to spend more time learning math, but how many of you could agree that from an educational perspective, it might be more interesting? We might have a chance to learn some more interesting things, to go into a level of depth where it kind of sticks a little bit more, right? And that's just the unfortunate truth of college level classes. We're all here, we're all got busy lives, and we have a certain time crunch that we're under. And I really, at the end of the day, it just makes it a little bit more difficult, the class. There's no doubting. So anyways, so if we had a little more time, we would go into base 10 numbers versus binary versus any number base. Okay, so this is the ones column, the tens column, hundreds. Notice there's no THs here. Thousands, 10,000s, but you could keep going. 100,000s, millions, 10 millions, 100 millions, billions, 10 billions, 100 billions, trillions, and so on. You can keep going and going and going. It just depends on how large of a number you have. So this is just a quick refresher. Now, once you get past the decimal point, it's going to go the opposite direction, but we don't start with a massive number here. Like this isn't the 100 trillionths, this is the tenths. And now notice the TH here, tenths. That's what allows us to know it's not the tens, it's past the decimal point, it's the tenths. And it's going to follow a similar pattern. Now this is the hundredths. Now this is the, what would you call it? The thousandths, excuse me. Thousandths. And so on. We're going to move all this up because I see I won't have enough space. Whatever. And so on. You can see that then this will be the 10 thousandths. Whew, that's a mouthful. And this one probably won't even fit on the screen, but this will be the 100 thousandths. And you can see we'll just have to do it like that. So this is just a quick reminder of what those places are called, because on your homework, sometimes you'll see round to 3 decimal points, which would be here. That would be your digit to be rounded. But sometimes they're just going to tell you round to the nearest hundredth. They may even tell you to round to the nearest whole number, which is your ones column. They may tell you to round to the nearest hundred or the nearest thousand, not without the TH. So you would replace everything to the right with zeros after you do your rounding. But once you're past the decimal point, you don't need zeros at the tail end. This 0 is important because there's still stuff to the right of it. But if I added any zeros at the right end of it, those zeros don't mean anything. They're meaningless. So that's a good little refresher on what the different places are called. So let's see. The world population, this was a couple years ago. I think the world population has probably crossed 8 billion by now, or getting close to it. World population, 7,476,242,056. Give or take probably a couple hundred or a couple million on that. Of course, you can't, can you ever accurately get the world population? I mean, the second you try to measure it, if it takes you a month to do the work, how many babies were born in that month? And how many people have passed away in that month as well? Not to mention, you know, maybe even in a premier first world country, whatever you want to call it, like the United States, the census is hard. The census is hard to do. There's millions and millions of people. They're constantly moving about. So this is all, this right now, 7,476,000, guarantee you that's just an estimate. And who knows if it's an underestimate or an overestimate, probably an underestimate. Anywho, if we want to round to the nearest 100 million, we got to figure out the 100 millions place. So this is 1, 10, hundreds, thousands, 10,000s, 100,000s, million, 10 million. There it is, 100 millions. That 4 there is our digit to be rounded. We look one place to the right of it, that's a 7. So we're going to be rounding up. So this 4 becomes a 5, and we replace everything afterwards with zeros. So 7,500,000,000 is an estimate of the world's population. Because we rounded up, it's actually an overestimate. You could also just say 7.5 billion. That's another way of saying the exact same number. If for some reason you only wanted to round to the nearest million, your millions place is right there. That's 6. Look one place to the right of it. That's a 2. Are you going to round up or down? Down. Because the 6 is a 6. But this is what we look at to tell us what to round the 6 to. Since it's less than 5, we round down. So we leave it as a 6, and then we replace everything to the right with zeros. Here, these zeros are necessary. They hold actual value. But if I did a decimal point and then, except it won't let me edit, but if I did put a decimal point and a bunch of zeros after the decimal point, those zeros are unnecessary. If you wanted to round to the nearest 100,000, have at it. That's the digit to be rounded is that 2. One place to the right is a 4, so we're rounding down. So everything to the right of your digit to be rounded is replaced with zeros. Pi, look, they used pi just like I did because it's just very difficult to resist pi. for rounding problems. Remember, we talked about pi. We talked about pi being a number that, like Limp Bizkit, keeps rolling, 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 rolling. It keeps going and going and going. It never stops, and it doesn't repeat. It doesn't have a repeating pattern. Thus, pi is an irrational number, we call it. So they tell you the first 7 digits of pi, because I can't possibly write out every digit of pi. It's has infinitely many digits, so it ain't gonna happen. So here's the first 7 digits of pi, the 3 and then 6 digits past the decimal. If you wanted to round to the nearest hundredth, you would look at the 4 here. One place to the right is a 1, so you round down. You don't need the zeros here, because again, zeros at the tail end after the decimal point, unnecessary. And so we can round to the nearest thousandth. So why do we bother with rounding? Why do we bother with rounding? Well, there's a couple really good reasons for it. Sometimes you don't need a ton of precision. There's no point in me asking how many of you have ever watched a show called Star Trek: The Next Generation, because probably none of you have, and that's okay. I used to watch. You watch Star Trek: The Next Generation? Give yourself a pat on the back. It's a great show, wonderful show. It's the one that has the bald captain, played by Patrick Stewart, who was also in the X-Men movies as Professor X. There's a character on Star Trek: The Next Generation who's an android named Data. An android's a robot, basically. He's trying to be human. And one of his funny little things he would always do, they're on the Starship Enterprise, and it's traveling at faster than light to some distant place. And the captain would come up and say, "Mr. Data, how long till we reach our destination?" And Data would say 3 days, 14 hours, 12 minutes, 22 seconds, 13 nanoseconds, and so on. He would give you way more information than you'd need. And Captain Picard would say, "Data, just say 3.5 days." So clearly there's a need for rounding, because you don't need absurd levels of precision. How many miles is it to our next destination? Look, is it going to be exactly 25 miles? No, it's probably 24.6821874 miles if you get out a really long measuring tape and you look at it very closely, but you don't need that much precision. It's absurd. You can round to a reasonable number and everybody's happy. So let's say you're at the store and you are purchasing some items: bread, detergent, sandwich. Hopefully you're keeping your items separate, because I've had a detergent sandwich and it's not fun. It's not fun. No, I've never had that. I've never consumed detergent, and I never will. Don't put that evil on me. I won't do it. Not even if every one of you dare me. Anyways, like I said, my jokes are lame. I used to be funny 10 years ago. People were like, "Josh, you're the king of comedy. You're so funny." Now it's just, you kids like to talk about old stuff like Star Trek. Nobody likes Star Trek, okay? Except it's awesome and you should like it. Therefore, I'm nobody. Anyway, so yes, I apologize for not being funny, but that's just life, okay? Would you rather have a math professor who at least attempted humor than one who just came up and didn't give you any at all? I think a little variety is something that should not be complained about. Anywho, so you purchase bread. The bread costs $2.59. The detergent is $5.17. The sandwich, $3.65. An apple for 47 cents. Well, that's a steal and a deal right there. Finally, you're getting coffee for $8.79. Hopefully that's not just a single cup of coffee. You're buying a bag of Folgers or whatever the other brands are, and hopefully you're getting some premium roast on that beans. Now your total bill comes out to $24.67. So if I just straight up add all these numbers up, even out to 2 decimal points, I get $24.67. What we might want to do is might want to get a quick estimate for the total cost. How many of you do that in your head when you're putting groceries into your cart? You want to make sure you don't go over, like, because if you're not paying attention and you get all the nice brands, you can drop $200 for like 5 days of groceries if you're not careful. So absolutely, this is something that happens to me. I always get to the checkout and I'm always like, man, did I really need that 12-pack of Full Throttle? The answer was yes, but I'm a little bit sad with my decision, because that's like $25. But anyways, so you're running a little total in your head, but are you going to run it out to 2 decimal points? Look, I'm not that good. I'm not even me. I'm a math teacher. I'm not that good with arithmetic. Nobody really needs to be. You know, you see a lot of videos of people who are called savants, meaning they can do, in this case, they can do really, really, really like absurd calculations all in their head. They can do like 37,516.384 times 2,521,287.9. They can do it all in their head in like a second. And it's not pre-coached. They get random numbers thrown at them and they can do the math behind it. And they don't have the numbers memorized or anything. Look, that's great. That's wonderful. I really wonder how valuable of a skill that is because mathematics is not about just punching numbers and doing calculations. Math is a whole lot more than that. And you probably realized that whenever we did linear inequalities, that you did almost very little calculations. Yeah, you had to solve the thing for one of the variables. But at the end of the day, you're not doing tons of number crunching all the time in math. There's concepts that you have to pay attention to. That's what math really is. So being able to crunch numbers quickly, I wonder how much of a real skill that is. It doesn't hurt, but you shouldn't spend a ton of time getting that skill. There's a lot of more valuable skills to get. So if you are running that total in your head, you might round the 259 bread, you might just round that to $3 to have a quick estimate. Detergent, you might round that to $5. You're rounding to the nearest whole number in each case. And now what we're going to do is with all these rounded values, maybe we can add those up quickly in our head. 3 plus 5 is 8, plus 4 is 12, plus 9 is 21. I think that's a reasonable system. We have to round the apple down to 0. Notice that in our rounding, we may have rounded down. Actually, it looks like we rounded up more than down. But I think rounding this apple down to 0 was damning. The total bill should have been $24.67. What you did, though, was you got $21 when you did it. This isn't right. This is supposed to be 0. So basically, the point is that you may have underestimated the total. You may have underestimated it. But that's okay. An estimate is still something. Now, the more items you add to your cart, you're not likely to buy 5 things when you do your big grocery shop. You might have like 30 things in your cart. The more you add those things up and do the estimate in your head, the less and less accurate it's going to be because each of the individual numbers has gotten further and further from its true value. When you add them all up, that all compounds together. But it's still good to be able to do some basic estimating, and rounding is one of your tools for that. So rounding is going to be an important aspect of estimation. There are other aspects of estimation that we ought to pay attention to. One of them is going to be circle graphs. Circle graphs, sometimes they're called pie charts, and notice they put that E on the end of it because it's truly talking about a pie, like something that you're cutting into slices, and not pi, the 3.14159 digit. So what these do is they take an entire quantity of something and they divide it into pieces. They say, okay, and they're rarely going to be all equally sized slices. And so you might do this with your budget. You might do this with your budget for the week. You say, all right, I've got $300 tops I can spend on the week after all my bills are paid and all this and that. This is what I'm spending each week for groceries, for random stuff that pops up. Hopefully car troubles don't pop up. Car troubles are the worst. Car troubles are the worst. When you hear a puttering sound in your car and you're like, I don't have the money to fix this thing, and it's annoying, and you just stress about it even when you're no longer driving, when you've successfully gotten to your destination. Then you worry, is this going to make me break down on the side of the road in the middle of nowhere? Car troubles are the worst. But let's say you have $300 in your budget for the week. You could cut that down into percents. You can say, okay, I just dropped $25 for a new softball shirt that my son needs. Okay, we spent $84 on getting some groceries that we needed for the week. We spent another $105 because we got Uber Eats, and Uber Eats for 4 people is expensive. Uber Eats is extremely expensive. It's like you get a $7 sandwich and suddenly it's a $30 just on Uber Eats because you got to tip your driver, you got to do all this. So you can take your weekly budget and you can cut it into the different pieces that you're devoting that money to, and thus you could create a circle graph for that. So on the next slide, we're going to look at a circle graph that indicates how Americans disagree to when old age begins. Basically, a survey is going to be handed out to some Americans, and the survey is going to ask a simple question. What do you define as old age? Is it a specific age that you hit, 60, 70? Is that considered old age? Is it when you retire? 32% of people who were surveyed said that they consider old age to be a decline in mental functioning. Of course, the concept of old age differs from person to person. It's fairly subjective. 41% said that old age is a decline of physical ability, where you can't get around like you used to. 3% say becoming a grandparent. Well, there's people who have grandchildren in their 40s and late 30s, some of them. And I definitely wouldn't say they're old. So that's why I think only a small percent of people call that old age. 9% say when you are retired, when you get to stop working. 1% said they didn't know. And then 14% said when you reach a specific age, like 60, 70, 80, something like that. So a circle graph is just useful in telling you how, the larger the pieces of the pie, the more prevalent they were among the population. The smaller the pieces of the pie, they weren't really all that important. Not that many people agreed with it. Yeah, we can do that. According to the U.S. Census Bureau, so this is the bureau of the U.S. government that counts people, that does demographic studies. How many people are in this age group? How many people are male, female, etc., different demographic categories. According to the U.S. Census Bureau, in 2016, there were 219,345,624 Americans that were 25 years of age and older. Assuming the circle graph on the previous slide is representative of this age group, in other words, assuming this circle graph is in play, calculate the number of Americans 25 years and older who define old age by a decline in physical ability. So an old age is a decline in physical ability. Well, we want the actual number of Americans. We know that 41% define it as a decline in physical ability. Now we want to know how many of these Americans here, the actual number. Guess what? Do we have to do this multiplication that we're about to do? Do we have to do it by hand? No. Do we have to sit down and try to think about it and do it in our heads? No. What do we now have access to? A calculator. That's right. So if you don't have a calculator today, that's okay. You can use your phone calculator for this, because you can't use one on an exam, obviously, but you can use a phone calculator for this. What we're going to do is we're going to take the 219,345,624 Americans that are in this age group, 25 and older. What we need to do is take 41% of that. To take a percent of a whole, you first convert your percent to the decimal, 0.41 in this case. And you multiply it by your total. And then we're probably going to have to round to the nearest whole person, because in truth, it's probably not exactly 41%. It's probably slightly different, and it was rounded to 41%. So what is 219,345,624 times 0.41? $705.84. So what we need to do, I'll put the 2 decimal points here. No. But these are human beings we're talking about. You can't have 0.84 of a human being. So it's just logical to round to nearest whole number. It just makes natural sense. In this case, that means rounding up to 89,931,706. So almost 90 million people age 25 and older say that, hey, you get old when you have a decline in physical ability. So they did that calculation. They ended up with, if we wanted to find a reasonable estimate though, if we just wanted to ballpark it, just get close to it, look, 41%, let's not do that to ourselves. Let's call that 0.4 instead of 0.4. Call it 0.4, you're close enough. Instead of 219,345,624, let's round that to the nearest 10 million, so 220 million. And then taking 40% of 220 million, maybe you don't need a calculator to do that. Maybe you can do that one by hand. Now, if you don't remember how to take percents of things, guess what? That's okay. Technically, we did cover it in 0332. We spent a little time on that. We converted percents to decimals and whatnot. But we're going to do that again here in 1332, and we're going to get to do it with calculators. So our lives are going to be made easier. So according to this estimate, about 88 million people define old age as a decline in physical ability. We calculated a little closer to 90 million, but we're in the right ballpark. It's all estimation anyways. You can talk about bar graphs. A bar graph doesn't quite do the same thing as a pie graph. What a bar graph does is it tells you how many, what the quantity is in different categories. So your life expectancy in the US, I believe we've looked at this bar graph before. Maybe we haven't, not in here. So here's how we read the bar graph. The height of the bar tells you what the quantity is of that category. Males are going to be red bars, females are going to be yellow. You come down here, you look at the birth year, the year that someone was born, and you can go figure out what their life expectancy was in that birth year. You can figure out what that life expectancy was. Your life expectancy is exactly what it sounds like. It's how old you're expected to be when you die. Now, very few people end up being that exact age. The point is that it's a kind of an average. On average, people born in 1950, males, have a life expectancy of 65.6 years. I wonder how they gather that data, because did they, in 1950, did they say it was that number? Because you can't predict technological changes. You can't predict changes to people's diets and health. So I wonder how this data is collected. Because here in 2020, they're saying it's this. You just kind of wonder. You wonder a little bit. Of course, unfortunately, I think because of the pandemic, life expectancy in 2020 might have dipped a little bit or not grown like it has been year over year. So just an interesting thought. So in 1950, a male had a life expectancy. He could expect to live 65.6 years if he was born in 1950. A female, though, could expect to live 71.1 years, almost 5 years longer. Wait a minute, ladies. You get to live longer than men on average? Yeah, that doesn't mean every woman and every man born at the same time, every woman will always outlive that man. It's just saying on average that will happen. That's due to a number of reasons. Some of the biggest ones are just genetics. Women tend to basically, just scientifically, they actually can store fat better than men do. Men don't store fat as well, which is actually a huge advantage, because it means that you can go longer periods without certain kinds of nourishment than men can. So it's kind of interesting. Men also have a really bad tendency of just dying from a heart attack when it's unexpected. Women, their heart health is a lot more predictable than men's heart health. My grandfather died at 70. He was at work and he went to the bathroom to use the bathroom, and he was standing on his feet and he died of a heart attack instantly. And that's how a lot of men go, a lot more often than women. So women just over the years have had a higher life expectancy. Now we're closing the gap a little bit because of better technology, better ability to treat heart disease in men than existed years ago. But women still have a little bit of an edge there. Incidentally, that's why life insurance is more expensive for men than it is for women. Simply because as a man, you're a little bit more likely than a woman to just pass away suddenly and require that life insurance, which pays out to your dependents, they call it, or your beneficiaries, rather. Yeah, beneficiaries. So I think that's a good stopping point for the day.